everyone. Welcome to another seminar of UT-ITE. Today we are joined by Dr. Willem Klumpenhouwer and Dr. Diego Silva. Dr. Willem is an postdoctoral fellow at the Transit Analytics Lab. His research focuses on performance analysis and modeling of urban transit systems, regional and intercity rail, and emerging technologies in the transit sector. He also builds open source data analytics and visualization tools to enable practitioners to manage, analyze, and evaluate their transportation systems more easily. Dr. William holds a PhD in transportation engineering from the University of Calgary and an honors Bachelor's of Science in theoretical physics from the University of Guelph. Dr. Silva has a PhD in computer science and currently he is a postdoctoral fellow at the Transit Analytics Lab at the University of Toronto. His research bridges between public transit and artificial intelligence. He is interested in connecting the cutting-edge computational methods to build better and more reliable mobility in cities. Welcome, Dr. Silva and Dr. William. The floor is all yours.
Great. Thank you. Thank you very much for that introduction. It's really good to be here. I'm happy to see a list of some familiar names that I've seen before, including some people you see on this screen right now. So Diego and I both worked on this project along with many other people. And so the way that we're going to do this presentation is I'm going to give you an overview of this transit center dashboard, sort of how it was put together, what went in it, what it does. And then Diego will zoom in on a specific challenge that we faced while we were building this project, which was to model fares. And so he will take over about halfway through the presentation and give you some more detail on some more technical detail on how that was done as well. Does that sound right, Diego? Sorry, I didn't mean to make you unmute there, but
yeah.
Great. Sounds good. And I think what we'll do is typically, you're welcome to put questions in the chat, but we'll probably wait for both myself and Diego to get through our presentations, and then we can have a discussion or some questions at the end. So I think that's the best way to do it. So you're welcome to go visit the sort of final project, the final product yourself. It's online at dashboard.transitcenter.org. And what it is a project that was funded by Transit Center, which is a large public transit advocacy group and organization in the United States. And they wanted a sort of a comprehensive look at access, which we'll get into, across 7 different US regions, and how that access is distributed among population groups. So we did this project with folks from U of T, so Lisa and Rick and Amer, you will see there listed. We also University of Toronto Scarborough, Jeff Allen and Stephen Farber from geography were a part of this, as well as folks from the University of Texas at Austin, which is Alex Carner, that he was the project lead, and Dana and Mitchell from the University of Vermont. So it was a big sort of collaborative effort to put this thing together, and the project took better part of a year, and you'll sort of see why. So in order to get started, I think the best thing to just get my slide to move. The best thing to start with is a quick definition of what we're talking about when we talk about access or accessibility. Those two terms are used somewhat interchangeably. It's important to note here, we're not talking about physical accessibility. We're not talking about the important part of transit, which is being able to make sort of barrier-free access for people to board and use transit. We're talking about a larger concept of access to opportunities. And there's 2 broad ways that you can measure this. It's basically a performance measure of a transit system. The first is to you take an origin point, which you have here as a yellow or an orange dot, and then you count all of the possible opportunities or destinations you can reach of a certain type, say jobs or cafes or any destination that you think is important. You count the total number that you can reach in a given set time. So, for example, you could say, how many blue blocks here can I reach in 45 minutes on transit? And you add them up, and that's your sort of access score for that origin. And then you move the origin somewhere else, and you do the same count, and you're going to get a different number for the same set of opportunities. And that's a different score or a different accessibility measure as well. So that's what we call cumulative opportunities or cumulative measures of access. Then there's the sort of reciprocal or the inverse, the dual as they call sometimes, which is to measure how long it takes you to get to the closest of a certain destination or the closest or the third closest destination. So for example, you may want to know how long it takes you to get to the third closest grocery store, in which case you would find the third closest grocery store and measure your travel time to it with transit, and then that would be your score. And you can see that represented here by green diamonds. You can see the third closest green diamond takes 18 minutes to get to in this particular diagram. And so they have there's different purposes and uses. There was actually a paper that was just produced about discussing when it's more appropriate to use one or the other. On the dashboard, you'll see both as well. But this is sort of the measure that we were trying to calculate for a lot of different destinations and regions. And so why is access important? Well, there are links between access, so having better access to destinations and having higher activity participation. There's a study done recently by Jeff Allen and Steve Farber, who looked at the TTS, at the Transportation Tomorrow Survey. They did a bunch of analysis, and they sort of found a connection between improved transit access and improved activity participation. So people, this is one of many benefits of having good transit access to opportunities, but people actually go out and do more things and participate more. And it matters. This is a Canadian context, but it matters because there's sort of a growing risk for Canadians of being at risk of transport-related social exclusion. And accessibility, specifically transit accessibility, can sort of eliminate the difference in daily activity participation between people who own cars or households with cars and households without cars. So it can really reduce the barrier in activity participation, which is sort of a generally positive and beneficial thing. This was again from Steve and Jeff's work, but low-income intersuburban neighborhoods tend to respond the most to transit investments in terms of increasing that kind of participation. So just sort of a brief idea of why this measure is important, because it is linked to positive outcomes as well. So let's talk for a minute about the dashboard, what it is, what we did with this project, and what all went into it. So there was a few sort of research questions that we had going into this, or as we went through this. We wanted to look at differences in access between socioeconomic groups. So this is the sort of equity aspect of the project. We wanted to look at, is there a systemic difference between access to opportunities for various socioeconomic and sociodemographic groups. While we started this project in March of 2020, the infamous March of 2020. Of course, COVID is on the mind. And so we adapted and adjusted our initial plan to start looking at sort of how changes made by agencies to transit schedules. So they were changing transit service in response to changing demand and various public health measures during COVID. How did that change access for people, and did it disproportionately affect different groups? So we looked at something over time as well. We also wanted to look at whether there was differences in access to various destination types. What does the city look like if you're interested in access to park space versus access to low-income jobs, right? So, where might there be spatial differences in those various destination types? We also wanted to provide a comparison between accessibility with a car or with an automobile and with transit, and sort of how different those access levels can be. And then finally, and this is where Diego is really going to dig into how we did this, we wanted to sort of see the effect of having a limited fare budget. So we were interested in, or Transit Center was interested in knowing, there's a lot of premium transit service in various regions, and in these 7 US regions listed at the bottom here, similar to Metrolinx's Go Rail, or just the Go Transit in general. And so we wanted to know, if you have a limited amount of money to spend on a fare in a given trip, how does that affect your ability to get to destinations? How many fewer jobs can you reach if you only have $4 to spend? So we'll get into that a little bit later as well. So in order to perform an accessibility analysis, what you really need is you need travel times. You need some sort of travel time matrix. We generated travel time matrices We traveled 2 travel time matrices. So the car travel time matrices came from Esri, Street Map, and Here data. It's the only part of this. It's the only part of this data set that isn't open source. Everything else was done with open data and produced with open source software. And then for transit travel times, we used Open Trip Planner, which is sort of an open source itinerary generator, and it lets you you load in a GTFS network or multiple GTFS networks for a region, and then you can calculate origin destination travel time matrices. So you need travel time matrices to understand how how far away something is or how much travel time there is. But you also need destinations, so you need to measure opportunities. So we pulled opportunities for all sorts of different categories from the U.S. Census. We looked at the food stamp program for grocery stores and SNAP retailers to sort of show access to food stamp retailers. We pulled some information directly from OpenStreetMap. So I believe the parks data that you see is pulled from OpenStreetMap, as well as some other US government sources on educational institutions and healthcare facilities as well. And then if you want to impose an additional constraint, which is that you have a fare as well, you need a fare matrix. And so what Diego really led was this large, huge undertaking to try and pull together an ability to create a fare matrix in a large region. And I will leave it at that. And so then once you have this accessibility score, you can look at who lives in the zone with a given accessibility, and you can see how that's distributed among various socioeconomic and sociodemographic groups. So you can use data from the census, and then you can start to see, is there equitable distribution of access to various opportunities or not? So that's sort of how the whole thing comes together. And we looked at a lot of different possibilities. So traditionally, or not traditionally, quite often, the focus when people do accessibility analysis, they typically look at access to jobs. It's a common use. Of course, you can look at any destination you want. Transit Center wanted sort of a wide variety of various options that you could look at. So we chose 9 different destination types. I won't list them, but you can see them on the website. For each of those destination types, there's typically 2 to 3 options. So for example, travel time, access to jobs in 30 minutes, 45 minutes, and 60 minutes by transit. Some of those measures included fare and not fare restricted measures. So there's another option. For most of the time, we measured 2 to 3 times a day. So we did a morning peak period during the week, we did a weekend service, and we did a late night service check as well. So you can sort of see how accessibility can vary for various times of day and days of the week. We did a comparison with auto travel times for a number of the measures as well. Each of these regions is divided into block groups, which is sort of the analog-ish of dissemination areas in the United States Census. And so the regions we looked at had anywhere between 3,000 and 14,000 block groups. So you can imagine an origin destination matrix, right? It's going to be, at most that squared. We just updated the dashboard actually with 2 new months. We originally did 12 months, and now there's 14 months worth of data up there across 7 regions. And so that generates a lot of data points, as you can imagine, because there's permutations of all of these things. We have well over 150 million different scores that we've calculated all over the place. So, and then you can see that the amount of agencies we had to include for various, so San Francisco, we modeled 35 different transit agencies. And New York City, you can see 47 million itineraries were checked for doing some of this modeling. So the problem or the challenge then becomes, how do you visualize this? And how do you sort of provide an interactive way for people to look at this data, at all the data points? And that's where the web dashboard comes in. And this was sort of my main thrust, and my main lead was putting together this visualization. So here's a screenshot. In fact, it's been updated a little bit. We're at version 1.1 now. So the legends will be a little bit different. But you can see a choropleth map of various transit scores, or transit accessibility scores, depending on what you choose here on the left side. So you can filter and update the map however you'd like. And then the week, you can sort of go through time with the timeline at the bottom, and you can jump from week to week as well. And so you can see how things sort of change over time. You can also overlay a demographic dot map. So you can see, they're a little bit faint, but you can see the dots here. And those dots, in this case, one dot represents 100 people living below the poverty line. And so it lets you compare sort of visually the scores with the demographic distribution of a specific group, so you can see where various things are clustered. And definitely in the United States, there's still a lot of segregation in cities of where Black people live, where white people live, and so you can see how that stark difference compared with the transit access score, might create some systemic issues. Here's just another example of New York. I think New York illustrates really well sort of the effect that, again, we're looking at, in this case, we're looking at a dual. So we're looking at closest grocery or third closest grocery store on a Saturday morning. So this is sort of coming up with the idea of maybe going grocery shopping Saturday morning, and you want to look at the third closest store because you want to have a little bit of options. You want to be able to pick from three grocery stores to go to. And so you can see that there is, access tends to spread out a little bit along the regional rail lines, which are represented by these black lines or these rapid transit lines as well. So you can see that sort of pushes access scores up nearby, assuming, and again, we're not applying a fare restriction here, so assuming that they're still affordable and attainable. Okay, and finally, there's also, we did regional summaries. So, we can take each individual block group score and weight it by the population of a certain demographic group that lives in that, and then we can summarize it. We can do a population weighted summary for the entire region. And so here you're looking at 4 charts, all from Washington, D.C. On the top left, we did a very simple measure of transit, what we call transit service intensity, which was simply just taking the total number of trips that pass within 200 meters of a block group and in a day, and dividing it by 24 to get an hourly average for the whole day, even though, so that was a way to account for span as well as frequency of service. And so you can see, the stark change in the number of trips per hour served in Washington, D.C. as COVID restrictions moved in. And then you can sort of see how it recovered, but never quite fully was restored. And then you can see how that translates into change in access. And so on the graph below, showing the same timeline. And so you can see there's a dip, and the dip is maybe less direct and stark, but you can look at the gaps between individuals. So in Washington, D.C., white people have higher transit access in general than other demographic groups. And that gap between, say, everyone and white did not narrow, and in some cases actually got bigger over the course of as service was restored. So this can help, start conversations about, was service restored equitably? Is there sort of a systemic problem in the way that that service is being designed, or access to opportunities at least is being conveyed? Top right, you can see a graph showing a comparison. This is for February 21st, 2021, comparison between average travel times to various destinations by car and by transit. So you can see, obviously, transit takes a lot longer, but again, the disparity between those two kind of emphasizes the point that, in many cases, transit is not necessarily as competitive of an option as it is with the car. And then finally, a histogram showing effectively the bar chart you see on the sides of these plots. These plots on the website, by the way, are interactive. You can click on different days and it'll update the ordering of the bars. And so this is just showing, the gap again in accessible jobs by transit in 45 minutes between white and everyone else, and it sort of shows an ordering of those various sociodemographic groups. Finally, quick sort of idea of how we use the fare. So Diego will talk about the fares in just a second. But effectively, what we did with the fare matrix was we looked at 2 sort of possible options. We looked at a network with every transit system in there, all the transit routes in there, and we looked at a network where we removed the expensive or premium transit routes, and we calculated an origin destination matrix for both, a fare matrix for both. And then using those 2 matrices, we can do a comparison. If you're trying to get from an origin to a destination, you may have 2 different options. So here on the bottom, you have a more expensive option that takes less time, and a less expensive option on the top that takes more time. And so as long as if you can reach your destination within a specified travel time, say 60 minutes or 45 minutes, and within a specified fare, then we can include that measure in what we call the fare limited access. And then you can sort of calculate the ratio. In this case, we did 1 minus the ratio to get a measure of fare disparity. So this is, what you can access when you have a limited budget versus what you can access if you have an unlimited budget. And on the bottom, again, these charts are all online for various cities. But again, in Washington, you can see the disparity between how much access there is to jobs with a budget and without a fare budget. You can also put them on maps. This is part of a paper that's currently under review with a number of us from the project. But again, you can put this fare disparity on maps. So darker means higher disparity, which means a larger sort of discrepancy between what you can access with an unlimited fare versus not. And so darker purple, higher fare disparity. And so you can see Brooklyn, for example, relatively low, but the borough of Queens relies more on more expensive premium sort of commuter rail. And you can see that commuter rail stretches out along Long Island there. And so you can see how these premium services induce disparity in what you can access. So the big takeaways here is access is, it's a great performance measure. It's a pretty comprehensive performance measure of a transit system. It connects transit planning. So the network obviously influences access, but so does the land use that you have and where locations are. This can be done with open data and open software. All of the data is downloadable. You can go and sort of look at a map you like and then download it and play with the data yourself. And all of it was done with open source software with the exception of the here data calculations. And then if you combine this accessibility score and population data with some visualization, you can start having some conversations about transit equity. That's it for my part. Diego, I hope I left you enough time. I think I did.
Yeah.
Great.
Sure.
So I'll stop sharing and I'll pass it off to you.
Okay. Thank you. Just 1 minute.
Yeah, no worries.
Okay. Can you see my screen?
Yep. Looks good.
Okay. So just let me test. Yeah. Okay. So thank you, Willem. The second part of our presentation describes a method developed to compute itinerary-based fares from adapted GTFS. So before diving into the method components, we have divided our agenda into 5 parts. So the first is the context and motivation, just a little bit. So just to increment what Willem mentioned. Then we explore the current gaps, how usually researchers include fares in their studies. And we frame our questions to define the boundaries of our scope. In the third part, we depict the solution, our interpretation of the fare network, architecture, simulation, and development. We then show the results and ultimately conclusions and next steps. As Willem mentioned, the analysis behind the dashboard uses emerging data source to reflect actual transit servers delivery in the US and how it meets the demands of different riders. Moreover, it uses a fare calculator to represent the reachable opportunities subject to budget constraints. In general, the cost to take transit is not commonly accounted for as a travel constraint in accessibility analysis. And to incorporate fares, we require knowledge about the fare paid for the shortest trip and some way to account for the possibility for of a longer, slower route between origin and destination that has a lower fare. If we impose a fare budget or constraint only on trips that can be completed in the shortest travel time, for example, a maximum of $4 for one-way trip, we are likely to miss feasible routes not on the shortest travel time path that stay within budget. Directly imposing a fare constraint on a set of shortest path travel time could inappropriately reduce a location's apparent access. So one approach to address this problem is simultaneously optimize fare and travel time. But unfortunately, this method is not easily incorporated into existing analysis tools or expandable to large, complex regions with multiple transit agencies. Another approach is incorporating the fare cost with travel time into a generalized cost structure. However, existing studies that explicitly include fares into generalized cost measures rely on locations with relatively simple fare structures. So in our study, we presented an itinerary-based fare calculation approach that is flexible due to its power to generalize complex rules, is scalable due to its integrated architecture, it's fast due to few elements to iterate over, and accurate that algorithmically represents arbitrary fare rules. And it is our focus in this presentation. Okay, so public transit has experienced significant transformations, and one that is easily perceived is the revolution in payment methods and onboard fare collection. So the benefits of fare systems extended beyond the payment automation process and provided significant performance and operational gains. Unfortunately, we have replaced the Hello driver with Hello Google, but modern systems can provide tons of data and several variables can be derived. Indeed, a crucial step to transit digitalization. So fares play an important role in the operational and financial well-being of transit systems. Most transit agents worldwide rely on fares, at least in part, to fund their daily operations. So fares are more than the fee we pay for the service. It comprises a complex set of interrelated factors, rules, and goals. For instance, payment type, demographics, distance, duration, quality of service, time period, technology. Moreover, the fare is constrained by formalized statements and guidelines for use in the service, also called fare policy. And what are these guidelines or statements? Well, some are posted on websites, which may or may not be easily accessible. Other transit agents have apps, but little information about agreements with other agencies or additional costs when using different media or transfer rules or exceptions. And in general, the information is decentralized and in different formats, which makes automated data extraction difficult. Some organizations have information about fares, but not the level of detail we were aiming for in our task. Another example is the National Transit Database, NTD, but it has average values like most other database and no information about transfers. In this slide, we see some examples, some formats. 2006 was a remarkable year for transit folks when Google released the first GTFS, and the fare files were there. However, the file is not mandatory. So the two files are limited in breadth of factors that they can efficiently describe and are ambiguous to implement. Furthermore, mapping multiple agents as fare in one GTFS is chaotic and has some limitations. Well, of the 139 agencies we mapped, less than 10% had the fare files. And those that did, usually the mapping was for cash only. Additionally, these files are mounted without an integrated view. It is impossible to know how the different fare systems are integrated within a region. These limitations are also a consequence of a non-data-oriented mindset in most transit agencies. We found issues in more than 50% of GTFS. So like duplicate agents ID, missing data, even mandatory fields were wrongly mapped. Recently, there has been an effort underway to create another standard for fares that contemplates their different structures and can be used at a regional level. Thus, we would have to build a database to map the fares. So this is one of the tasks. In addition, we would have to find a data representation that could be generalized to maximum number of agencies in multiple regions, considering the different fare structures, integrations, and transfer rules, and open source. But wait, aren't you we reinventing the wheel. Well, we are not, and I'll explain why. Because we have three different options in terms of architecture. Now it's software architecture. So the first one would be ideal, but we didn't choose it due to the limitations of the current GTFS version. So limited ability to express complex fare structures, and in many cases, missing data. The second option would be to build the fare files from scratch. However, we would still have data representation issues, and we would have to modify OTP to interpret the new files automatically. So it's too risky. The third option was to use the GTFS integrated into the OTP and use its output to calculate the fares as a second step. So the fare mapping task was inevitable. So we used the knowledge from mapping the fare rules website by website to create the calculator using a test-driven development method. So we built test case to validate the fares and guide software development. The beginning of development is slower with this method, but it tends to accelerate from the middle to the end. And the quality result is significantly higher with this approach. Okay, so now let's talk about the method. We can define fares theoretically, as we did in the previous slide, but tracking all those factors for modeling is impractical. We reframe it starting from the idea that the fare is a set of permissions. Moreover, the permissions are activated or deactivated as we traverse some points in the system that can be physical, such as transfer points or stops, or logical. For example, maximum transfers or maximum duration, which means that the transit fares layer partially overlaps the physical transit infrastructure, but is not necessarily the same. In this example, let us consider a passenger who will pay the fare using a card. We first generate an arbitrary itinerary on OpenTrip Planner. Then we calculate the fare for the first leg on step 2. As you can see, there is a flag equal to 0. So this flag is like a sentinel, and it will warn the next leg if there's a valid permission to be used. I represented it as a bulb to show that it has only 2 states, so 0 or 1. At each iteration, we check whether the rules are still valid within the boundaries of each permission, so max transfer and max duration. We update them, and then we repeat the process for each consecutive mode pairs. We always iterate in pairs. So if the flag is 1, there is a valid transfer rule. If it's 0, means no transfer rules. And when the flag is 0, the passenger needs to pay the full fare. Each iteration generates a partial cost that we sum up when we reach the last leg of the trip. Okay, so this is the first part of the solution. The second part was the mapping step. So we mapped rules, values, transfer, gratuities, exceptions of the 139 agencies in our study. So the first step was to classify the fare structures into continuous, zonal, and special fares. For continuous, we mean a predefined ratio or constant value, for example, distance-based fares and flat fares. Continuous fares are the most commonly used fare structure, as they are simple and easy to comprehend. Zonal fares group transit stops or stations into geographic or political zones. So transit users pay according to the number of zones traveled. And special fares are unique models or combinations of fare structures. So they are often the most difficult to model, as rules are usually unclear, and fare information is unavailable, where special condition must be considered for an accurate data representation. Then we extracted the information from the website visited one by one. Yeah. So the critical element for more realistic fare was mapping transfer rules. we mapped over 40,000 rules. And this is because we had to make permutations to be applied correctly on each trip leg or mode interaction. The transfer rules were also grouped into 4 levels. So between agencies, for example, TTC. TTC users get free transfers on IRT. And it does not matter which bus. So this rule would be applied for any bus in the system. Rules between modes, like bus to bus, subway to subway, or bus to subway. For example, at the route level, Route 1 has a transfer of $1 to Route 2. Finally, at the stop level, passengers who board at a particular bus stop do not pay the transfer. Furthermore, we mapped the rules as a function of mandatory fields in GTFS. It allowed us to avoid adding many fields to describe each fare structure. Only the essential ones for mapping the value and duration and transfer amount and payment type and region fields. The algorithm also tracks the duration, the number of transfers, and the permission status on each iteration. So this is one example we found on the transit agent's website. So we identify the keywords in the sentence, and we encode them into our adapted file, and then we run the scripts. So this is the architecture view, and in blue are the scripts in the fare calculator. So first we generate trips on OTP. So the fare function receives the trip file and the region ID. The mode function adjusts the itinerary for posterior partial cost computation. The fare sort functions updates, activates, or deactivates transfer rules for each initial leg and underlying pair. And moreover, the function controls the flag status. We also built a new database model to reflect the solution, but it has some opportunities to be optimized. And finally, the transfer function sorts transfer rules and returns a subset of permissions available for the pair within the iteration process. As I mentioned, there were 139 transit agencies distributed in 7 regions. The development started with the New York region, as it covered a variety of fare structures in the code that we reused in other regions. As I mentioned, our approach was test-driven development, where we created a set of positive and negative test cases that covered most of the trips variations, approximately 350 test cases, to validate the software behavior. The accuracy ranged from 81% to an exact solution in Chicago, for example, which is relatively high considering the task difficulty. The challenge was not necessarily the number of agencies in the region, but the complexity of the fare structure, the transfers, and the availability of reliable information. Philadelphia was an example. Despite fewer agencies, the fare policy information was not publicly available on the website, and a linear regression was our choice to estimate fare for New Jersey transit. So mapping regional fares are challenging due to decentralized information and unclear agency rules. Fares vary based on multiple factors that may hardly encompass unique standard without significantly increasing the set of fare attributes. Instead of adapting the solution to attend a plethora of fare structures, we mapped each permission using mandatory fields in GTFS, extending its well-known benefits. As agencies incorporate more factors into their fare models, our solution tends to become more limited. So the next steps are, the method has proved a suitable approximation and is ready to be replicated in other cities or regions. To incorporate additional factors such as environmental equity indicators, for example, to leverage the discussion towards transit equity by accounting detailed and realistic transit fares over simulated itineraries, and to provide additional constraints to studies on transit demands, dynamics, and route choice. So these are our reference, and thank you for your time.